Welcome back to the channel, Adventures Through Climate Change, with your host, me, Trevor. Yes, and today we are watching a video. Sometimes we read articles, sometimes we watch videos. Whatever we're doing, we're taking an armchair approach and trying to figure out what's happening in climate change. So please join us. These are unedited videos. So sometimes I say stupid things. That's just how it goes. Yeah, it's today. Let's check this out because, you know, I actually, somebody was mentioning, hey, you should talk about the atmosphere and stuff because you talk about CO2 and whatnot. I was like, hey, that's a good idea. This is the Bozeman Science channel from 7 years ago. I don't know how much has changed on the idea of the atmosphere. I did read an article like a month or two ago that was like on the atmosphere that was saying that it may be a lot larger than we experience because how this works, you know, in space with the vacuums and whatnot, in interstellar space, you know, is a lot more of a vacuum than intrastellar or like inside our solar system or whatever. And so our atmosphere, you know, there's probably like some layers of particles that, along with like the satellites and all that stuff, that are going around our Earth in some degree, form or another. And the atmosphere, you know, might just extend past the moon, past onto another planet where the other planet's atmosphere goes into ours. I don't really know. It was just this article. It's kind of interesting. But with that being said, let's kind of get into this. This is about a 12-minute, almost 13-minute there video. And hopefully I got my sound corrected. Thank you for the help from y'all, and sorry for the weeks of bad audio. I'm terribly sorry. Terribly.
Hi, it's Mr. Anderson, and this is Environmental Science. Video 4, it's on the atmosphere, which is the gas covering on our planet. Remember, we live in the atmosphere, and as society gets larger, we're pushing against these planetary boundaries. And since the economy is pushing us towards that, the economy is going to have to bring us back. And a story that relates to this is the story of stratospheric ozone. We call that good ozone. It's made of 3 oxygen atoms, and it surrounds the planet, and it protects us from harmful UV radiation. But in the 60s and 70s, we were producing huge amount of CFCs. A CFC is this is an example. It's a carbon, fluorine, 3 chlorine molecules. It would also go into the atmosphere, get hit by UV radiation, kicks off a chlorine, binds to an oxygen atom, and now we've destroyed the ozone. And so you've probably heard of this hole in the ozone. This one's right here over Antarctica. What's going to happen if we don't have that protective ozone? Increase in cancer, damage to crops, and so this is a really big deal. And so how do we solve that problem? Industry is going to say, rightly so, we shouldn't have to bear the cost of all of this. It's going to cost us, you know, millions if not $1 billion. We're going to lose jobs. But eventually the consensus came around and government said, we're going to have to solve this problem. And in 1987, they signed on to what's called the Montreal Protocol, where they banned CFCs. That's led to a decrease in CFCs, increase now of ozone. It'll probably return to its original levels by 2050. And so this is a great example of how governments can bind together to form a treaty that's incredibly successful. And so the atmosphere surrounds the Earth. Scientists break it into a number of different spheres. We've got the tropostrato, meso, thermo, and exosphere. Now, we live in the troposphere, and that protective ozone is going to be found right at this boundary between the two. Weather is going to be the current state of our atmosphere, and over a long period of time we call that climate, which is due to the tilt of our axis and where we are in the orbit around the sun. And so due to our location, we get seasons. We're pointed towards the sun in the summer and away from the sun in the winter. But also, since we're a sphere, we're starting to get unequal heating of the planet, and those convection currents lead to cells in the atmosphere. Got things like the Hadley cell, the Ferrel cell, and what those are doing is moving the atmosphere around on our planet. Now, we also have a spinning planet, and that creates something called the Coriolis effect, and so it spins in a characteristic way. And so the combination of these two lead to atmospheric circulation. It's moving the weather around on our planet. Now, the oceans also affect our climate, and as the atmosphere moves around, it starts to move the oceans. And so we get these ocean currents, which are shaping our climate. And an example of all these things coming together is El Nino, or ENSO, the El Nino Southern Oscillation, sun, which we'll talk about in a little bit. And so the atmosphere is a series of spheres that surround our planet. This is not to scale, but the lowest one's going to be the troposphere. That's where our mountains are. That's where we are. When you're on a jet, you're still within the troposphere. Above that, we're going to have the stratosphere, so weather balloons will move into that area. If we look at ozone right here, so this is going to be ozone right at the surface of the planet. We're going to have some bad ozone. We call that tropospheric or smog ozone that can be damaging to us. We'll talk about that later. But as we move up in the troposphere into the stratosphere, we're going to have a huge increase in that ozone layer. That's that protective layer around us. Above the stratosphere, we have the mesosphere. That's where meteors are burning up. Above that, we have where the aurora are. That's going to be the thermosphere. And then finally, we're bordering space. This is going to be the exosphere up here. Now, what are some conditions within the whole atmosphere? We're going to increase density the closer we get to the Earth because there's higher gravitational pull the closer we are. Now, what's the atmosphere like today? That's weather. Raining, is it sunny? What's the temperature? And that's important. But what's more important is climate. That's going to be weather over a long period of time. And if we look at this biome map, you start to see some patterns. And so if you look right here, we're going to have a bunch of tropical rainforests. We'll have deserts right here. And if I put the latitudes over this, the one thing I'm always surprised is how low the equator is. So if we put this in at 0 degrees, then 30, and then 60, real patterns start to emerge. So right here along the equator, we're going to have all of this precipitation. Rainforests are going to be found there. But look right here.
And I'm sorry to interrupt him. We'll give him a little bit more time. We'll go back. But I want to point this out because we watched a few videos over the last few months that talked about how it only really freezes when you have an ice age on the northern side. And you could see literally like right in this middle zone right here. I mean, this is the equator, right? So if all the land masses are above the equator, except for not as many down here, this is going to be the area where the snow resides. It's where it sits. It's where it's gonna accumulate, right, on top of the water, or I mean on top of the off the water, on top of the land, and most of the land is up north. That's why. So I just wanted to point that out because I was like, okay, we've been watching this and talking about this, you know.
Along the equator, we're going to have all of this precipitation. Rainforests are going to be found there. But look right here at 30 degrees above and below, or northern and southern, we're going to have these deserts. And then we're going to have these big boreal forests out here. And so all of that has to do with where the Earth is in orbit and also the tilt of the Earth. And so we get seasons due to the tilt of the Earth as it moves around the sun. This is obviously not to scale, but as the northern hemisphere is pointed towards the sun, look here on the North Pole, it's going to be 24 hours of daylight. In the winter, it's going to be 24 hours of night. Right here we'd have the equinoxes, but depending on are we pointed towards the sun summer or away from the sun winter, it's going to affect our weather and therefore our climate. Remember, everything would be reversed if we were in the southern hemisphere. We also get unequal heating. So if I, again, not to scale, but if I were to put an atmosphere in here, as the sun's rays come in here, at this part, it's going through a very small amount of the atmosphere, so we don't lose much heat. But up here, we're going through more of the atmosphere. It's going to be colder near the top. If we remove that and just look at the light itself, right here, this amount of sun rays is all concentrated on this very small surface area, but up here near the North Pole, it's spread out over a long surface area, a large surface area. So it's going to be cooler near the poles. Now remember, as we move around the sun, that axis is going to tilt back and forth, and so that's going to affect this unequal heating. And the last thing that affects unequal heating is the albedo of the Earth. It's our reflectiveness. So as the sunlight hits the snow, for example, it's going to be reflected off. But if it hits vegetation or water, for example, we're going to have a different amount of albedo. So it's a combination of all of these things that creates climate. First one that's most important are going to be the cells on our planet. What that means is right here at the equator, we're heating up the air most right here along this point, and so what we get are these convection cells. So we heat up the air and it's moving up. It becomes less dense and it's moving up. Now what quickly happens to it is it actually cools down. And so as it cools down, we eventually reach something called the dew point. That's where it can't hold water anymore, and we're going to have the formation of clouds, and then we're going to have precipitation. Have you ever wondered why the bottoms of all the clouds line up? It's because we're cooling the air as it moves up until we hit that dew point. Now what happens eventually is that atmosphere is going to start to drop down again. And so we have another cell here and another cell here. So if we look at the equator, we're going to have a huge amount of precipitation here. But remember, at around 30 degrees, all that air is moving down. It actually is being heated up, and we're not going to have much precipitation there or at the pole itself. And so these will be affected by the tilt of the Earth as well. And so cells are important to understand. So I've turned the Earth on its side. So this is now equator, North Pole. So if we move from the equator to the North Pole, the first thing we see is a huge amount of convection near the equator, and you're going to have a huge amount of weather right here. It'll eventually move up, and then it slides down. As it moves down, it's going to actually heat up, and we're not going to have much precipitation at 30 degrees. We call this first one the Hadley cell. It's named in honor of the person who proposed it. Now if we keep moving, so again we're moving down to this next cell right here, we're also going to have convection current that's moving the air up at 60 degrees north latitude and south. And then eventually it's going to be heated as it moves down. So we're going to have more precipitation here. We call this the Ferrel cell. It's named in honor of the person who proposed it. And then finally we have a polar cell. It's named in honor of, no, it's not. It's just near the pole. And so the other thing that contributes to a cell,
so
it's named in honor of.
At 30 degrees, both of them just go down. Precipitation only goes down. There's nothing rising up from there. You have a combination effect at 30 degrees north. That's interesting, because even at the North Pole, it pulls it from 60. Anywho.
Or the person who proposed it. And then finally we have a polar cell. It's named in honor of, no, it's not. It's just near the pole. And so the other thing that contributes to atmospheric circulation is Coriolis effect. So again, the Earth is spinning. Think of it like a record player spinning around. If I were to tape something to the record player, like this cone, let's say it represents the mountains, as the record player spins, the mountains are just going to move around with the Earth. We're moving on the Earth right now. We are not affected by it because we're connected to the Earth. But let's say I put something on that record player that's movable. Let's say I put a marble on it, and now I spin it. Watch what happens to the marble. It will be deflected off. And if I were to trace that path, it moves like this. And so if you think about it, on the north side of the record, it's going to be moving clockwise. But if you could move underneath the record, it would actually be moving counterclockwise. And so the Earth is like that record player. It's a sphere, obviously, but in the northern hemisphere, it's going to move clockwise. In the southern hemisphere, it's going to move counterclockwise. And so the combination of these cells and the Coriolis effect creates the weather patterns that we have on our planet. So you can see here are the three cells, Hadley, Ferrel, and polar cells right here, but we also have the movement due to the spin of the Earth. And so right here near the equator, we're going to have what are called the trade winds. They're always going to be moving in this direction due to the spin of the Earth. Both in the southern and northern hemisphere, they're all moving in this direction. If we move north or south, we're going to start to get what are called the westerlies. It's going to be moving in this direction. Now, as that atmosphere pushes on the ocean, we get oceanic currents. We're getting these trade winds, and then we're getting the westerlies coming back. As that blows on the ocean, we get this Gulf Stream that's moving the ocean. We also start to get deep currents in the ocean due to heat, but also due to changes in salinity. And so this ocean is moving around as a consequence of not only salt, but also the temperature. And so tying these all together, something you should be very familiar with is ENSO, or the El Nino Southern Oscillation. And what really is going on is it's just moving back and forth between El Nino and La Nina. And so this is a graph that shows this oscillation from 1880 to 2010. And so it's in a neutral position. It will then move towards El Nino, and then it'll move back to La Nina. And then it'll move to El Nino. Sometimes it's not a very big El Nino. Sometimes it's a very big El Nino or La Nina. It just moves back and forth. So it's oscillating. You can see that in the record. But you should be asking yourself, well, what causes it? And so let's go look. And so we're looking at is the Pacific Ocean. So this is the Pacific Ocean right here. This would be Central America, South America, North America. And then all the way on the other side of the Pacific is going to be Australia over here. And so what we have is a Walker circulation. Remember, the trade winds are blowing the wind in this direction along the equator. And as they do that, what we get is a circulation pattern that moves the ocean water, cold water here, it's pushing the warm water to the western Pacific. This is the neutral or the normal position. Now, what can happen Watch what happens to the Walker circulation as I move us into a La Nina. So as I move us into La Nina, watch what happens to the Walker circulation. We have greater trade winds. An increase in trade winds is pushing more of that warm water over here towards Australia. So we're going to get that weather way over here. It's going to be cooler here around Central America. Now watch what happens when the Walker circulation starts to die off. Now we have El Nino. And so we don't have that huge push. And so we're going to have warm weather. It actually starts to move in the opposite direction. And so this ocean is now going to affect the atmosphere, and it's going to affect humanity as well. So
but he didn't mention, and this I think we said this was like 7 years ago. This was a number of years ago, this video. But he didn't mention the fact that we've had 3 La Ninas in a row, right? The cooling one. That's the cooling one, I believe. And why that Walker circulation effect doesn't affect that. Why do you have 3 in a row sometimes? And opposite. So you can have, I think, 3 El Ninos in a row, and it really messes with the atmosphere. But usually year to year, it goes back and forth because of that, supposedly, that Walker circulation. I don't know. I don't know.
Affect the atmosphere, and it's going to affect humanity as well. So could you fill in this concept map? I would encourage you to pause the video and give it a try, and then I'll tell you the answers. First thing, could you tell me the levels inside the atmosphere? It's troposphere, stratosphere, mesosphere, thermosphere, so that should be here. Exosphere. My mnemonic for this is try some milk, then eggs. That's a good way to remember the layers. Right here, we'd have that important ozone gas, which can be bad if we have it way down here in the troposphere. Weather over a long period of time is going to be the climate, which is affected by the tilt of the Earth and the sun and the location of the sun. So we get seasons from that. We also get unequal heating, which creates these convection cells, Hadley cell, Ferrel cell, polar cell. The spin of the Earth creates the Coriolis effect, and also ocean can impact that. So hopefully you got all those right, and I hope that was helpful.
I gotta say, I really enjoyed this guy's videos. Is he still making videos? 7 years ago. It's got 1 million views. He's got to be still making videos. And he doesn't have one play right off the bat. That's so nice. I'm rude like that. 9 years ago, 11 years ago. Wow. So he's still making stuff. Man, this guy, he just seems so cool. Okay. These videos look very, looks like he's taken a step backwards from the actual video portion where he used to kind of just pop himself in there, right? And now he's just doing that. Anyways, I'm sorry. I digress, guys. What do I think of the video? Honestly, I thought, wow, it popped for something that I didn't. I thought he was going to go more into the atmosphere because that's what the video was about. I didn't think it went into the atmosphere as much as it probably could have, but the thing is, it talked about everything, just a little bit of everything that we've been talking about. So it's kind of neat. It was like putting all this stuff together, and he's just kind of clicking and talking along and whatnot. But interesting. I thought it was a great video. Bozeman Science, probably out of Montana would be my guess. You guys tell me. Look, I would always love your subscription, but if you can only give one, give it to him. I'm subscribed to him. I like the video. I gotta give people credit because they're the ones making the videos. I'm just I'm not pirating. What I'm trying to do is consolidate and bring focus to both sides of the argument and create discussion. That's what I'm trying to do. I'm not monetizing this channel, so I'm not trying to steal anybody's material. So if you want to give them the benefit of the doubt and go, watch their videos and stuff, I totally understand. I'm just trying to get a discussion going. So with that being said, I do love your comments because then it puts me in a direction. I don't reply very often anymore. I was for a while, but then I got super busy. But I do read them. I read through them, and every now and then if one really hits me, I'll reply. And so with that being said, I hope to catch you on the next video.